one important topic. This is set theory, or you can say the sets. And first of all, we'll do some theoretical explanation and then we'll continue with related problems. So this is also important topic in abstract algebra. And you will see most of the time at least one question has been taken from set theory in the examination of B.Sc, IIT JEE, NBS, KVS, EMRS, BMath, etc. So now we'll continue with the definition of the set. So what is the definition of set? So set is a collection of well defined distinct objects. So as for example, set of all prime numbers less than 10 less than 10. So that means that will be 2, 3, 5, 7. So these are the set of all prime numbers less than 10. Generally, a set can be written as in a capital letter. So you can write set is set of all primes p less than 10 in that notation, where 2, 3, 5, 7 are the element of the set p. Okay. So there are two forms of the set. So now note, when we will represent the set, we will use the capital letter. Say capital letter is equals to small a, b, c. What exactly mean? That means A is the element of S. You will write A belongs to S, and B belongs to S, and C belongs to S. Okay. Note 2, note 1, note 2. The classification of set, we can write two kinds of set. One is set, note 2, set forms of set. Forms of set. There are two forms of set. One is called set builder form, set builder form, and another kind is roster form. Roster form. I'll give you an example. Say if we consider, as for example, S equals to all those real number such that x greater than equals to 0. Okay, and say x is an integer. This is basically the set builder form. If we represent it in the roster form, so that can be written as 0, 1, 2, 3, 4, and so on. So this is basically the roster form, and this is basically the set builder form. So now we come to some important set. So as for example, set of all natural numbers. Okay, some important set. 1, set of all natural numbers. All natural numbers. So this set will represent by n, or you can write in that way n. In some book you will see this symbol, some book you will see this type. So what is the meaning of the set of natural number? This is a universal symbol. This is 1, 2, 3, 4, and 5, and so on. Next to set of whole numbers. Set of whole numbers. that is represented by the symbol W, and here W means 0, 1, 2, 3, and so on. For the set of all integer 3, Z that is represent this is basically called set of all integers. All integers. That means it is 0, plus minus 1, plus minus 2, plus minus 3, and so on. Next, set of all rational number that is represented by Q. Q is basically set of all rational number. Rational number. And this is basically of the form P by Q, where P and Q are integer with Q not equals to 0. This is the definition of set of all rational number. And set of all irrational number. Next, Q complement, or sometimes it represented by I. This is basically set of all irrational number. Irrational number. Okay. Whereas you will see this type of root 2, root 3, that pattern e, pi, pi to the power e, and so on. This number is basically the set of irrational number. Now we will come to the set of real number. This is represented by R, or in some book you will see this symbol is taken as R. So this is basically set of all real numbers. Real numbers. Okay. And that is one important note. If we see after some times when we'll give the concept of subset and union, on that time you will see set of natural number is a subset of set of whole number. Set of whole number is a subset of set of integer. Set of integer is subset of set of rational number. Set of rational number is a subset of set of real numbers. And you will see set of rational number union, set of irrational number. This is basically set of real number. Now that is another important set. This is called C. C means set of all complex number. Set of all complex number. Complex number. So that means this is basically in the form of A plus IB, where A, B both are real number, and iota, this is basically root under minus 1. So that is basically set of complex number. Now, there are different types of set that we will discuss here. Recall types of sets. Types of sets. First is the empty set. Empty set. Empty set. Sometimes we are called it null set. In some book you will see it the void set. So empty set that is represented by phi, and that contains no element. Okay, so this set is called empty set. So a set is called empty set, called empty set, or null set, or void set. Void set if it contains no element. It contains no element. Okay, and it is denoted by, and it is denoted by phi. That means phi, this is basically, so no element is there. Next, we think about the proper subset, or you can say, okay, you can think about the finite set. Finite set, that means a set is called finite set, is called finite set if it contains contains finite number of elements. Finite number of elements. So as for example, so the finite set we can write a1, a2 dot dot an. This is an example of a finite set. Finite set. So here you will see the cardinality of the set A, or you can say the number of elements in the set A is n, which is finite in numbers. Otherwise we call it, finite number, it contains finite number of elements. Otherwise we call it infinite set. So infinite set means if a set contains infinite number of elements. So example of an infinite set is a set of natural number 1, 2, 3, 4. Set of integers 0 plus minus 1 plus minus 2. All are example of an infinite set. That is another concept that is called the subset. Subset. What exactly mean by the subset? So subset is basically, sometimes the symbol is like this or symbol is like this. So let A and B be any two non-empty set, sets, then A will be subset of B if and only if for all x belongs to A, it implies x belongs to B. Or you can write x belongs to A implies x belongs to B. This is for all x belongs to A. Okay, so that will be the definition of the subset. And here A is a subset of B and B is called the superset of A. Note, here B is called a superset of A. That is, B is superset of A. In that way we can write the same thing, but you can call it with respect to subset and superset. So I'll give you one example. Say your A set is contained element 1 and 2 and B contains element 1, 2, 3. So here you will see every element of A obviously belongs to B. So that means A is a subset of B in that example. Now we'll continue. Another important, here also another note, every set is a subset of itself. So A subset of A for any set A, that we can say. And we also say empty set is always subset of A for any set A, or for every set A. That results are basically true. Now we come to another important concept here. This is called the proper subset. Proper subset. Okay. A is proper subset. That symbol is represented by this. So this is the symbol is a proper subset of B. That means there exists an element in B which is not in A. So that means this is your B, this is your A. Obviously in that diagram a subset of B, but there exists an element X X is basically belongs to B but not belongs to A. Okay. So proper subset means for subset and there exists an element X belongs to B but X does not belong to A. If we satisfy these two cases, then we call A is proper subset of B. Now, when two set will be equal? Equal sets. Equal set. So let A and B be any two set, then A will be equal to B if and only if A is subset of B and B is also subset of B. Then we say that both are equal. That means every element in A must belongs to B and every element in B must belongs to A. Now, there is another important concept. This is called the singleton set. Singleton set. So, when a set is called singleton, is called singleton set if it contains only one element. If it contains only one element. As for example, say S is just contain 0 or maybe S1, S2 just contain 1. So these are the example of singleton, single element, singleton set. Now we come to the algebraic operation of sets. Next concept is algebraic operation on sets. Okay, first we'll think about all the things we will think about with the help of Venn diagram. Okay, so first is union of two sets. The first concept is union of two sets. Okay, and union symbol is basically represented by this. Let A and B be any two sets, then the union of A and B is denoted by A union B and is defined by A union B. That means all those X such that X belongs to either A or X belongs to B or both. So or means either in A or in B or both. So here the note. So if say T belongs to A union B, what exactly it means? It means T belongs to A or T belongs to okay. And if we draw the Venn diagram here, you will see that this set is A and this set is B. This set is B, this is A, this is B, and this is the universal set, maybe U, or you can consider X, no problem. So the whole place is called the union. This is basically A union. That part as well as that part. So this whole part is basically A union. Now we come to second important operation. This is the intersection. Intersection of two sets. Intersection symbol is like this. Let A and B be any two sets, then the intersection of A and B is denoted by A intersection B and is defined by A intersection B equals to all those x such that x belongs to A and x belongs to B. So here if we draw the diagram, this is A, this is B, A and B. So intersection means that place. That place comes under the intersection. So this is basically A intersection. Okay. So here the note is x belongs to A intersection B. What exactly it means? X belongs to A and x belongs to B. And that means x belongs to both A and B. That comes under the intersection. And here another note, you must verify here. The whole thing is the union. This is the intersection part. So intersection A intersection B, this is always subset of A union. Okay. Now we think about difference of two sets. Next, concept 3, next operation, difference of two sets. So here we can set an example for intersection and union, then we will continue the difference. So as for example, your A is basically say 1, 2, 3 and B is basically 2, 3, 4, 5. So now if we draw the diagram is here, this is your A and this is your B. So A contains 1, 2, 3, B contains 2, 3, 4, 5. Let's see here A intersection B, this is basically 2, 3. Okay. That means that 2 belongs to A and 2 belongs to B. That means 2 belongs to A intersection. Again, if we take for the union, so your example, your A is 1, 2, 3 and say B is 2, 3, 4, 5. So what will be union? There will be 2, 3, 1, 4, 5. So A union B, that will be 1, 2, 3, 4, 5. Now we come to the difference of two sets. Let A and B be any two sets. The difference of the difference of A and B is denoted by and B is denoted by A minus B. Or you can write set theoretic notation like this and is defined by A minus B that belongs to all those x such that x belongs to A but x does not belongs to B. This is the symbol of does not. You know this symbol is for belongs to and this symbol of not belongs to. This is belongs to and this is not belongs to. Okay. Now you will see the Venn diagram what exactly mean. And you will see the way this is a universal set. This is your A, and this set is your B. So A and this is B. So that part is basically called the A minus B. This part. So this part is basically called A minus B. That means all elements which belongs to X, but not all those X, such that X belongs to A, but X does not belongs to. Similarly, we can say difference of A from B, that will be B minus A, or you can write in that way. That means all those X such that X belongs to B, but X does not belongs to. I'll give you the example. Say your A set is 1, 2, 3 and B set is 2, 3, 5. So now if we consider A minus B, that means all those elements which belongs to A, you can draw the diagram is here. So here 1, 2, 3 and B is 2, 3, 5. So A minus B contains that portion. So that means A minus B will be singleton set 1, whereas B minus A, that will be 5. Okay. So you can write either this symbol or this symbol. So in that way you can calculate A minus B and B minus A. So now here we get the one important. So again, if we draw the diagram, till now we have done A union B. A union B, that means the whole thing. The whole thing comes under the A union B. This is your A that represent your B. Now what is the intersection? The intersection is basically that part comes under the intersection. This belongs to the intersection. So this is basically A intersection. Now if we think that this part, so this is basically A minus B. A minus B. And if we think about that one, that part, this part is basically B minus A. B minus A. Now we get the relation between union, intersection and difference. A union B, this is the first, the green portion, that means A minus B union. Then the intersection part, red part, that means A intersection B, and union, the blue part, that means B minus. So this relation is very, very important. This relation is one of the important relation, and that relates union, intersection and the difference. So with the Venn diagram, we can easily find out this relation, or we can establish the relation in an easier way. Now we come to the fourth concept, operation. This is the symmetric difference. Symmetric difference of two sets. Difference of two sets. And let A and B be any two sets, then the symmetric difference, is denoted by of A and B is denoted by a symmetric symbol like triangle, symmetric difference A and B, and is defined by a symmetric difference B. This is basically A minus B union B minus A. Okay. So that means if we draw the diagram, this is your A and this is your B. So that part is basically A minus B, and this part is basically B minus A. If we take union of these two, that means A minus B and B minus A, that will make the symmetric difference. Union of blue and red here means the symmetric difference A union. And that also can be written as A union B minus A intersection. The whole thing minus the intersection part. That means that part. That part is basically intersection part. That will be again the symmetric difference that you can visualize with the help of Venn diagram. Okay. So if we calculate the symmetric difference, here I will give you one example. One example for symmetric difference. So A is again 1, 2, 3 and B is say 2, 3, 4. So obviously A symmetric difference, that will be A minus B union B minus A. A minus B, that means if you draw the diagram, this is your 2, 3, here 1, here 4, this is A, this is B. This is the diagram. So A minus B, that means 1 union B minus A, that means 4, that means 1 comma 4. So this is basically a symmetric difference. So symmetric difference, that operation is done. Now we will do the Cartesian product. Next operation is the Cartesian product. Or you can say the product of two sets. The product means the Cartesian product, or you can say the product of two sets. Okay. Now we'll move to the definition. Let A and B be any two sets, then the Cartesian product of A and B is denoted by A Cartesian product B, that way, and is defined by, and so here we can take A and B be any two non-empty set. Otherwise the Cartesian product will be meaningless. And is defined by a Cartesian product B, that means it should be a ordered pair XY such that X belongs to A and Y belongs to B. So just like an ordered pair. So here the note 1, say if you have seen XY belongs to a Cartesian product B, that implies X belongs to A and Y belongs to B. If we see the Y comma X belongs to a Cartesian product B, that means Y belongs to A and X belongs to B. So first element comes from first set and second element will take from the second set. Okay. But that is important note, a Cartesian product B may not be equal with B Cartesian product. As for example, so you have given A equals to 1, 2 and B equals to 3, 4. So what will be a Cartesian product B? That contains 1, 3, 1, 4, 2, 3, 2, 4. Whereas B Cartesian product A, that will be 3, 1, 3, 2, 4, 1, 4, 4. And here you observe A Cartesian product B, this is not equals to B Cartesian product. But one thing is common. The cardinality of these two sets are same. Okay, but the note is A Cartesian product B, that cardinality must be equal to B Cartesian product A for any two non-empty sets A and B. Next note, if cardinality of A equals to M, that means it contains M elements, and cardinality of B, that is the number of element B, is N, if then you will see the Cartesian product A and B that contains Mn elements. And this is also the element in the Cartesian product B Cartesian product A. Now we will continue another operation. This operation is called set of set, or you can say the power set, or sometimes it is said as set of sets. So set of sets, how we will define? Let A be any set, then the power set of A, is denoted by capital P bracket A, and is defined by power set of A equals to all those sets B such that B is a subset of A. That means set of all subsets of A. This is called the power set. So one important note here, phi, the empty set always belongs to the power set of A. So here I'll give you one example. Say your set A is 1, 2. The question is, what should be the power set of A? So power set of A, that means it can phi, singleton set 1, singleton set 2, and 1 to itself. This is the power set of A. And the question is, if A equals to phi, that means empty set, if, then what will be the power set of A? So power set of A must contain the phi and the set phi itself. So that is the power set of A. Okay. So that will be simply phi. So what is exactly, that is one important formula. The formula is not if cardinality of a set is n, then number of elements in power set of A, that means the cardinality of the set power set, this is 2 to the power. So here the example, if A contains 4 elements, then the power set of A, that cardinality will be 2 to the power 4, that means 16. So this result is very important. In some cases, we must know what should be the power set of. Now this is your exercise. Exercise. If A equals to 5, then you will calculate power set of power set of power set of that you will calculate. And you will say, our next question is, you will calculate, you will say power set of A, what should be the cardinality of the set. So this is given as an exercise to you. Now we'll do some important law in the power set, not the power set, in set. So there are many laws in the set theory. You can consider the properties of sets. Properties of sets. Okay. So what are the properties of a set? First property is related to the idempotent law. We'll do the many more law here. Idempotent law. What exactly mean by the idempotent law? Let A be any set. The idempotent law says us A intersection A, that will be A, and you also say U union A, this is also A. Not only that, if you do the intersection A n times, again that will be A. Or if you do the union n times, union of A, this is n times, again it will be A. Now we come to the next important property. This is called the commutative law. Commutative law, you can prove all this law, but okay, you need to recall all this law. Commutative law, that means A intersection with respect to intersection, that will be B intersection A. And if you take the union B and you take the B union A, this is also same. So this is called the commutative law. Now next law is called the associative law. Associative law. So what is associative law? A union B union C, that will be A union B union C. And A intersection B intersection C, that will be A intersection B intersection. So this law is called the associative law. There is another important law. This law is called the distributive law. Distributive law. So distributive law says us A union say B intersection C, that will be A union B intersection A union C, and A intersection B union C, that will be A intersection B union A intersection. So this law is called the distributive law. So we must recall all the laws, and all the laws are very much important in our examination. Next is another important law. This is called absorptive law. Absorptive law. And this law says that A union A intersection B, that will be A. That means that intersection we absorb. You can visualize with the help of Venn diagram. And if we say A intersection A union B, again it will be A. So this law is basically called absorptive law. Like here A is absorbing intersection. In the next case, A is again absorbing A union B. And there is also one famous law which is called De Morgan's law. Next law number 7. This is called De Morgan's law. What the law says? The law says if we take A union B whole complement, that will be A complement intersection B complement. And A intersection B complement, that will be A complement union B complement. But here we just forgotten the operation about the complement. So what is called the complementary sets? So choice 6 and 7 complementaries. Set, or you can say complement of a set. Complement of a set. So let A be any set, then the complement of A is denoted by A complement and is defined by A complement means all those x such that x does not belong to. Okay. So here the note is x belongs to A complement. What is the meaning? The meaning is x does not belong to. Okay. So as for example, if A is the set 1 to 3, so then we can say 4 does not belong to A. And that implies 4 belongs to A complement. So in Venn diagram, this is a universal set. U is the universal set, and this is our A. Now the question is, what is A complement here? For that universal set, A complement is this part. This part except A part, these are belongs to A complement. So this part is basically A complement. A complement means here U minus A. The universal set minus the set A is called A complement. So this is A complement and this is A. Okay. So this green part is basically A complement. Now I said the different law, the law idempotent law, commutative law, associative law, distributive law, absorptive law, and De Morgan's law. But here we will prove the De Morgan's law. That is one important question in graduation level. They prove that the question is prove that De Morgan's law. De Morgan's law. Or the question is state and prove the De Morgan's law. So this kind of question has been asked in graduation level. It is for 5 marks. How to prove? So first we will give about the statement of the De Morgan's law. So now statement, let A comma B be any two sets, then A intersection B that complement equals to A complement union B complement, and A union B that complement equals to A complement intersection B complement. This is basically the De Morgan's. Now how to prove? So that we consider Roman 1 and Roman 2. Now we will do the proof. The proof is for the first case, just to think about to set how to show P equals to Q. First you will show P subset of Q, then you will show Q subset of P, and from that we can conclude P equals to Q. Okay, so here we we have to prove that intersection B whole complement equals to A complement intersection B complement. So just we have taken an element X belongs to A intersection B whole complement. And what we will show here, we will show from that set X belongs to A complement intersection B complement. This is our target. Okay. So from this information, then what we can write, X does not belongs to A intersection B. And what exactly mean by this? That means X does not belongs to A, or I said the intersection, or X does not belongs to X does not belongs to. And from that we can write X belongs to A complement or X belongs to B complement. Okay, I'll start from the first case. So here I will show union, or X belongs to B complement. And from that we can write X belongs to A complement or means union B complement. So what we have proved here? We have proved, so therefore X belongs to A intersection B whole complement implies X belongs to A complement union B complement. So A intersection B complement, this is subset of A complement union B complement. Now we will continue the second one. Not second one, this is Roman one. Now we'll take, let X belongs to A complement union B complement. And we will show here X belongs to A intersection B whole complement. So what exactly mean? That means X belongs to A complement or B complement. So that means here X does not belongs to A or Y, X does not belongs to B. And from that you can write X does not belongs to A intersection B. And here we can write X belongs to intersection B complement. So therefore here we have proved A complement union B complement subset of union B whole complement. So this is true. So from 1 and 2 we conclude A intersection B whole complement equals to A complement union B. In similar way you can prove 2. This is your self exercise. Thank you so much.